For this example, I'm going to find the eigenvalues and eigenvectors of this matrix, minus 1, 0, 0, minus 3, 1, minus 2, minus 3, 2, minus 3. As always, we start by finding the determinant of A minus lambda I to give us the eigenvalues for this matrix, which we get by subtracting lambda off the diagonal of the matrix. To find this, we'll expand along row 1. There's only one non-zero thing in that row. So what does that give us? Well, that gives us that this determinant equals negative 1 to the 1 plus 1, negative 1 minus lambda, times the determinant of the opposite minor, which is these four down here. 1 minus lambda minus 2, 2 minus 3 minus lambda. That's a 2 by 2, so let's work it out. Minus 1 minus lambda times that for the 2 by 2. We expand out the inside. I have lambda squared. I have plus 3 minus 1 is plus 2 lambda. Minus 3 plus 4 is plus 1. Well, that's lambda plus 1 squared. Minus 1 minus lambda times lambda plus 1 quantity squared. But since minus 1 minus lambda is negative lambda plus 1, this is actually just negative lambda plus 1 cubed. So we have lambda equals minus 1 is a triple eigenvalue. We only have one thing to check here, just that one eigenvalue. Let's see what we get. For lambda equals minus 1, when I do A plus I get the following. 0, 0, 0, minus 3, 2, minus 2, minus 3, 2, minus 2. You can probably see what's going to happen with the row reduction. If I swap rows 1 and 3, and then do row 2 is row 2 minus row 1, I get 2 full rows of zeros here. So where do we go from here? Well, we only get one equation for our three unknowns. We only know that negative 3v1 plus 2v2 minus 2v3 must be 0. What can we do with this? Well, we can look back at our ideas of free variables here. So in this matrix, I only have one pivot column. So I only have one not all zero row, and it's the minus 3 here. So both the second and third column are non-pivot, so both v2 and v3 are free variables. So I can pick anything I want for both of them. And since I have two free variables, I should get two linearly independent eigenvectors here. And I get that by making sure I pick different things, and by different I mean linearly independent things, for v2 and v3 for my two choices. So I'm going to recommend doing the following. I'm going to say for option 1, we're going to set v2 to be 0 and v3 to be 1. Now, the main thing here is I need them all to not be 0. So I pick one 0 and the other to be 1. Now it's going to be different from if I pick v2 to be 1 and v3 to be 0, which is going to be my other option here. So in that case, when I plug into my equation, I get that negative 3v1 plus 2v2 minus 2v3, which need to be 0. Well, v2 is 0, so that's gone. And v3 is 1. So I end up with minus 3v1 minus 2 equals 0. v3v1 equals 2. v1 is negative 2/3. So from that I get the eigenvector minus 2/3, 0, 1. Now my option 2 here is to pick v3 to be 0 and v2 to be non-zero. So v2 will be 1 and v3 will be 0. If I do that, I then get minus 3v1 plus 2v2 minus 2v3 equals 0. v3 is 0, so that's gone. v2 is going to be 1. I'm left with minus 3v1 plus 2 equals 0. Negative 3v1 equals minus 2. v1 equals positive 2/3. And so my eigenvector here is 2/3, 1, and 0. So what do I conclude from all of this? Well, I conclude that for lambda equals 1, there are two linearly independent eigenvectors. Examples are the two that I gave. Minus 2/3, 0, 1, and 2/3, 1, 0. Now, it turns out that these eigenvectors, it forms a two-dimensional space of vectors. So any linear combination of these two is still an eigenvector for the same eigenvalue. So if you'd picked other numbers, you get different things. For instance, the vector 0, 1, 1 is also an eigenvector. Also, this lambda equals -1, not +1. That's just adding the two together. You get 0 on the top, 1 and 1. For any choice of v2 and v3, as long as you make two linearly independent choices for those vectors, you will get a basis for this full set of eigenvectors here. There are many, many options that work. Eventually, there's a skill that comes up with picking the right one for your case, but in this case, this works out just fine. As a final note, this is still a defective eigenvalue. Why is that? Well, I did get two independent eigenvectors, so my geometric multiplicity is 2, but if I go back to the first part, the algebraic multiplicity was 3. The power here is 3. I only got 2 eigenvectors, so I'm still technically short by 1, which means it's still a defective eigenvalue. There's an example of how you can solve for these eigenvectors in the repeated eigenvalue case, particularly when you have a two-dimensional set of eigenvectors, how you can get it from the matrix and how that relates to the defect of these eigenvalues in the repeated case.